In the previous video, we saw the z-test method for testing a particular hypothesis, and it was mainly used for testing the mean. Now, let us go further and see some more tests. The t-test. So, like a z-test, t-test also assumes a normal distribution of the sample, and t-test is used when the population parameters, you do not know the mean and standard deviation of the population. So, you only have the sample data. So, in such a case, we want to do something with the sample data is when we use the t-test. It is also used to test whether there is a significance difference between the means of two groups. So, I have group A and group B. Both have a sample size, and I have two means, the mean of group A and the mean of group B, and I want to know whether the difference is significant. So, t tables can be used for this, and we have t scores which are given for a certain degree of freedom. We will see what this is. What is the meaning of degree of freedom is the number of independent values that can vary in a sample, the number of independent values that can vary in a sample. So, here since we do not know the standard deviation, we need to calculate it. So, this is the formula for you to calculate the standard deviation. I have put a S here, S means the sample. So, you have the readings you have taken from the sample. So, from those readings you calculate the standard deviation of the sample. So, that is given by sigma xi, sigma of xi, xi is the sample value minus x bar is the mean sample value whole squared divided by n minus 1 under root. So, I think you can get an idea what is happening is it is giving you the average deviation from the mean value, something like that. It depends on the average deviation from the mean value. So, this is how the standard deviation is calculated. Now, there are different types of t tests under different conditions. We will see what it is. So, the first one is one sample. It is called as t-test for one sample. So, in one sample test, one sample means what? It is not just one unit, one group or whatever. One sample you have taken, it can consist of 100 people, 500 experiments, 10 stores. In one sample test, we want to compare the mean of a sample with a known reference mean, something similar to our z-test with a known reference mean. For example, a manufacturer of chocolate bars claims that its chocolate bars weigh 50 grams on average. So, I say I have a chocolate, homemade chocolate I am selling, and it has, each bar has 50 grams. Now, I want to test whether the shopkeeper is saying the truth or not. So, I test 30 bars at random and I get a mean value of 48 grams, right. So, now can I say that this mean value of 48 grams is significantly different from the claimed 50 grams, or is it okay? Is it acceptable? So, here in one sample test, the degree of freedom is given by n minus 1. The degree of freedom is given by n minus 1. Now, in general, the t factor, like we have the z factor was x bar minus mu by sigma by root n, like that we have a t factor. It is a difference between mean values divided by standard deviation from the mean. This is called as the standard error. So, this is what it is. So, for the one sample, the formula is very similar to what we have used. for z factor, z x bar minus mu divided by s by root of n. Here s is sigma, the standard deviation. Now, if I am using a finite population, right, I use the formula x minus mu h naught, that is mu, sigma s by root n. Why sigma s? Remember, I do not know the population standard deviation. I know only the sample standard deviation. So, standard deviation, we use s, we use sigma. I have put both so that you get familiar with different nomenclatures. N is the population size, n is the sample size. You remember in Z test we saw, if I have 20 stores, I choose 5 of them. So, the population size and the sample size are comparable. So, that time we use this formula. This is a t test for a single sample. Then you have, that is how you define the t factor. Then you have t test for independent samples. So, for independent samples, what we are doing is, we are comparing the means of 2 independent groups of samples, and I want to know whether there is a significant difference. For example, I sample 100 people in one group and another 100 people in another group. I find their average height is say 170 centimeters, and here the average height is 165 centimeters. Now, I want to see whether this difference in the sample size I have chosen, that is of 100, is significant or not. This is the t test for independent samples. Or supposing I want to compare the efficacy of 2 drugs, A and B, that time I will use this. So, I am basically in this, I am going to compare 2 samples. So, here what is the t factor I use? How is it defined? x1 bar, that is the mean of sample 1, x2 bar, mean of sample 2, divided by root of standard deviation of sample 1, standard deviation of sample 2, divided by n1 and n2. This is the formula you are going to use to calculate the t factor. Clear? So, I have 2 painkillers A and B, and I claim so I do a test. Painkiller A, it sustains, a single painkiller if I take, it sustains for 8 hours, and painkiller B sustains for let us say 7 hours and 40 minutes. So, do I conclude, how do I conclude that these means are comparable, they are similar or not? So, I use this t factor. Same, like in Z test, here also you have some critical factors, we will see how you can get it. Then I have a paired sample t test. So, this t test is used for dependent samples, is used to compare the means of 2 dependent groups. So, I have an effective diet. To do this, I weigh 30 people before and after the diet. You remember in random research design, we had before and after. So, how can you verify those tests? This is what we do. And exactly the same people after the diet. So, with a paired sample t test, we only need to calculate the difference of the paired values and calculate the mean from that. So, the standard error is then same as in the t test for one sample. So, xd bar, mean of the difference between what? Difference between people who have taken the diet and who have not taken, or before the diet and after the diet, the difference. 0 because I am doing the test. So, there is no difference without the test. So, that is why the other mu is 0. Standard deviation and number of cases. So, here I am trying to test a dependent variable like weight loss, how it is dependent on the diet, clear, or some health parameter, maybe acid reflux and diet, something I want to compare. So, that time I use this paired sample t test. So, here the sample is the same, right, The sample is the same and I compare its performance before and after the treatment, and use a T definition as this, and then see whether the hypothesis is valid or not, whether you reject it or accept it. The null hypothesis, alternative hypothesis, all are similar. So, level of significance or level of confidence, nothing changes. That is independent of the test. They are all general terms used with hypothesis testing. So, now you have, so here the degrees of freedom is again n minus 1. Okay. So, you have what are called as standard T tables, standard or T, they are called as T score tables or T value table. So, the table would look something like this. So, let us try to understand this table. Let us try to understand this table. Okay. So, here I have two-tailed test, same like my hypothesis. If I just say not equal to, then it means it can be less than or greater than. Then I use a single-tailed, where I have in the alternative hypothesis only less than or only greater than, and I compare the magnitude here, because there are no negative numbers here, there are only the magnitudes, right. So, this gives you the level of significance for two-tailed test. So, this is 20%, 10%, 5%, 2% and 1%. So, 20% means very narrow, very precise, okay, and 1% means not precise, it will be flattened, something like that. Similarly, I have the level of significance for one-tailed test. This is the significant values. Now, here I have this factor, difference factor, n dependency factor n minus 1, n1 plus n2 minus 1 and so on. So, I can calculate the DF for a given problem, and I know how to calculate the T, right. Then if it is less than this magnitude, accept H naught. If it is greater than this critical values, reject H naught. Incidentally, these tables will go on. You will have, then you will have 50, 60, 80. So, here initially there is a difference of 1, 2, 3 single unit, then it will go in a difference of 10, then you will have 100, 500, 1000, infinity. So, we will see with examples how you can use it. As your sample size becomes larger, you go on using the relevant number. Now, let us take up different examples for this t-test. A company wants to improve its sales. Look at the problems here, okay, and compare it with what we did for z-test. The previous sales data indicated that the average sale was $50 per transaction. After training 25 salesmen, the recent data showed an average sale of $80 per transaction. If the standard deviation is $15, has the training provided improved sales? So, in this case I do not have to go for a t-test because I know the standard deviation. Remember, standard deviation is when you do not know, you can go for a simple z-test. So, what do I do? How do I hypothesize? So, I hypothesize that the mean is 50 and I want to show that training has increased. So, it has increased. So, alternative hypothesis will be mu is going to be greater than 50. Understand the problem here. So, I know the average value has been 50. I have not trained all sample. I have trained only some 25 of the salesmen. I have not trained all the salesmen. So, by training 25 salesmen, I have found that the transaction value has increased to $80 per transaction. So, can I conclude that this training program is good? It is going to increase the mean. So, you should know how to formulate the hypothesis, right. So, what do I hypothesize? I hypothesize that it is 50, that is it is equal to the old value, and after training it will increase to 50, greater than 50. mu is greater than 50, right. Now, so what is Z? 80 minus 50, okay, 80 is the new one, sampled mean is 80, population mean is 50, divided by standard deviation is 15, and I have taken 25 samples, so root n is 5, that is 10. 10. Okay. So, with 5% significance, the critical value of Z is 1.64 for single tailed, So, this value I have got Z equal to 10 is greater than 1.64. So, what do? I reject H naught. So, whenever the value of Z is greater than the critical value, you reject the null hypothesis, that is the test. So, I reject H naught means I accept HA, So, I accept HA means what? The transaction is greater than 50. So, what can I conclude? I can conclude that the training program has increased the sales. Therefore, the management can go ahead using this training program for all the salesmen. You see where this kind of a test is useful, not just take number and then reject and all. After that, based on that, you have to take a decision. So, the management will say, okay, with this sample 25, we have proved that this training is effective in increasing the sales. So, let us train all the salesmen using this training program. Clear? Now, consider the next problem. The average weight of men in a region is 191 pounds, some region, let us say South India, and the mean weight of 100 men chosen was 197 pounds with a standard deviation of 25.6. With a standard deviation of 25.6. Can we accept the hypothesis? Hypothesis means what? What is the hypothesis I want to show? That this average weight of 191 applies to these people also. Or another way of saying is, I can say that the sample of these 100 men, come from the same population whose average was 191 pounds. So, whether I have sampled correctly or not. So, now let us see how we propose the hypothesis. So, what is my hypothesis? Mu is 191 and HA, mu is not equal to 191. Now, here we do not know the standard deviation of the entire population, we only know it for the sample. So, for this sample of 100 men, the standard deviation is 25.6, we know that. Okay. So, I can use Z when I know the population standard deviation. Here I know the sample standard deviation, so I will use the t-score. Formula is the same. The mean of the sample 197.1, the mean of the population 191 divided by standard deviation of the sample 25.6 and square root of the sample size 100. So, root 100 is 10, 2.38. Okay. So, now let us look at the Z table. This is the Z table. Now, my DF is 99, it is 100 minus 1, 99. I do not have an entry for 99, I will use the entry for 100. So, just see how to use the T table, right. This is the T table, right, 100 and significance. So, I will be using the one tailed if I want greater than or I can use 2 tails. So, here look at the values, it is okay. Let us take the 1 tail. So, this is 1% and this is 0.5%, this is 1% and this is 0.5%. So, this value is 2.364 and this value is 2.628. Now, let us see what was my Z value. My Z value was 2.38, sorry, not Z, T. My T value was 2.38. Now, look at this, 2.38 is somewhere very close to this, right, very slightly different. So, I can say that I can accept it, I can accept it because it lies, you know, within the acceptable region. 2.38 is less than 2.626. Okay. So, therefore, what do I conclude? What do I conclude? We find that this lies between 1% and 0.5%. You saw, no? If you use here 1 tail, if you use, it lies between 1% and 0.5%. 2.38 is in between these two. So, with that significance level, I can accept. So, with this significant level, I can accept H naught. But 1% means it is not very precise. 1% is not very precise. A higher significance level means more precise, but more probability of rejecting H naught when it is true. So, there is nothing wrong in your result if you say that it is acceptable with a significant level between 0.5% to 1%, you can say that. Or you can say it is rejected. If I say, if the whole thing I say, take a standard significant level of 5%, then you are going to reject, because for 5% if you see, yeah, for 5% here the value is 1.66. The critical value is 1.66 for 5% and your T factor is 2.38. So, it is above the critical value, so you have to reject it. So, this hypothesis, what is the hypothesis again? The hypothesis that the sampled men came from the same population as the original is rejected at a significance level of 5%, but is accepted at a significant level of 1%, right. So, whether you want 5% or 1%, that you have to decide on how critical your decision is, clear. There are no standard rules, it will depend on your problem. Now, with Z-score tables, there is you get like T-score, you get a Z-score table also. Normally in Z-score what happens, we remember only 2 values, 5%, 1%, it is 1.96 and 1.64, you can easily remember. But you also get a Z table and we will see where this is useful. So, a Z-score table shows the percentage of values, usually a decimal figure, to the left of a given Z-score on a standard normal distribution. What does this mean? For example, if my score is 1.09, 1.09 is the Z-score, then how do I get 1.09? This is my Z table, just see here, this is 1 and this is 0.09. So, this entry is 1.09 is 0.86214. So, you know this Z is 0, right, this is 0 and these are all positive and these are all negative. So, if this is 0.86214, this means the area covered to the left of a Z of 1.09 is 86.21%, that is the meaning. That is the meaning. So, to the right obviously is the remaining portion, it will be 1 minus 0.86214. So, basically from the Z score table, you can make out for a given Z value how much percentage lies to left and how much percentage lies to right. Now, we will see where this could be useful, in some kind of problems and in some research problems this can be used. We will see where. Now, look at this. Find the probability that a variable has a Z score less than 0.36. Find the probability that a variable has a Z score less than 0.36. Now, you go here, 0.3, set 0.3, 0.06. So, this value is 0.36, 0.6406. What does this mean? 0.6406 means what? 64%. So, this somewhere here you will have 0.36, 0.36 will be here. So, 64% lies to the left. You know, everything to the left is acceptable. In one side everything to the left is acceptable. So, that means what? 64% chance is there that the Z score will be acceptable, because 64% chance is there that it will lie on the left side. Got it? Now, another place where you can use it, just see here. A normally distributed population of test scores has a mean of 80 and a standard deviation of 5.2. So, let us say it is a class. In a class, I give a test, and this is my result as a teacher. The whatever I have taken, that sample, the mean is 80 and the standard deviation is 5.2. Now, we will answer some questions from this data if it is possible. Find the percentage of scores that lies below 73. How many lie below 73? How many lie above 73? And say in between 82 and 86, or in between some number you can get. So, for these kind of problems also you can use the Z score table, very interesting. So, when you do a research sampling, right, you can give all these results. You can say this many, the probability, I mean percentage of people who are likely to have got more than 73 is so much, less than 73 is so much, and lying in between 82 and 86 is so much. And then supposing they ask you the question, what is the percentage of people who got above 90, anything you can answer. You can do a lot of data analysis in a very simple way. So, see how you can apply this. Now, first 73, the Z score of 73 is, sample mean is 73, population mean is 80 divided by 5.2, divide by 5.2. Okay. Only one sample I have, one. I have not said how many people and all that. So, you take it as a unit, one unit. So, n is 1. So, minus 1.34615. Now, in the Z table, so I need 1.34, I can't go beyond two digits. So, minus 1.3 is here, you can see here minus 1.3 and 0.04. So, this entry will be corresponding to minus 1.34, it is 0.0901. 0.0901. So, how much is that? That is the percentage to the left, that means less than. Therefore, so 0.09 is 9%, 9.01% below 73. So, out of that sample, the percentage of people, average is 80, mean is 80, mean is 80. So, the percentage of people who have got below 73 is 9.01%. Obviously, those who got above 73 will be 100 minus 9.01, that is 90.99%, right. Now, there is the third part of the question, how many have got between 82 and 86? So, the Z score of 86 is 1.1538 and the Z score of 82 is 0.3846. So, the numbers from the Z score corresponding to this Z value is 0.8749 and to the left of 82 is 0.6480. So, these two numbers I got it from similarly how I got the previous case from the Z score table. So, the area in between is this. So, that means 22.69% got in between 86 and 82, right. Now, I advise you to try out, you try out your own values, how many got less than 60, randomly try out with the same data, that is 80 samples, the standard deviation, just do it and then the mean is 80 with a standard deviation given, try out how many got less than 60, greater than 60, how many got above 90, whether there is somebody who got above 40. So, you will find that that who got below 40, if you take, it will be very less because it is very much away from the mean. Similarly, above 90, 95, that will also be less. So, you can get very good idea from this, okay. A very simple tool to do a lot of analysis with data, especially when your sample size is large, you can do a lot of data with this, data analysis with this. This is another use of Z table. Next, okay. A sample of 100 tires is taken from a lot. I have a tire manufacturing company, I take 100 tires randomly and the mean life of tires is found to be, for these tires, for these 100 tires, the mean life is found to be 39,350 kilometers with a deviation of 3,260 kilometers, standard deviation of that. This is my sample, okay. Now, the manufacturer is claiming that these tires come from a population whose mean life is 40,000 kilometers. So, with 99% confidence, establish whether this is right or wrong. That means, you have to say whether this sample is from a population whose mean life is 40,000. You have not observed 40,000, you have observed 39,350. So, the claim is it is 40,000, observed sampled is 39,450. So, you should be very clear what number you put in the hypothesis, okay. Now, in the hypothesis I am putting 40,000, not 350. Why? Because 40,000 is the original population. I want to show that this batch has come from that or not, or what if the manufacturer or maybe the dealer has just put in some old used tires in between, one or two of a couple of them, so that we do not know. So, we want to verify that, right, fine. So, H naught mean is 40,000, HA mu is not 40,000, that means it comes from another batch. So, now I do not know the standard deviation of the entire population, but I know the standard deviation of the sample. So, I will use the t-test. Remember always, when you know the standard deviation of the entire population, use the z-test. When you know the standard deviation of the sample, use the t-test, right. So, confidence level is 99% means significance level is 1, because I am confident 99% it is true means 1% I take the risk of it being false. So, 1% significance level. Okay. Now, so T is the sample mean, that is 39350, minus the claimed mean or the population mean is 40,000, divided by standard deviation is 3260, and I have tested 100. So, root n is 10, I get minus 1.99, minus 1.99. Okay. Now, we already saw in the t test, where is the t test? Yeah, here. The t scores for 100, right, with 1% significance level, it is 2.626. It is 2.626. So, what do I conclude? This 1.99 is not greater than 2.62. So, the critical value is 2.62 and my value is less than that, it is 1.99. So, I accept the hypothesis. So, I accept the hypothesis. Which hypothesis? Null hypothesis. Always remember, acceptance or rejection is only for the test is for the null hypothesis. If you accept it, automatically it means you are rejecting the alternative hypothesis. If you reject it, means automatically you are accepting the alternative hypothesis. Clear? So, I accept the null hypothesis. So, what can I conclude? I can conclude that my sample of 100 tires has been taken from a lot of tires which have a mean life of 40,000 kilometers. So, if the company owner, tire manufacturer comes and says, I have an average life of 40,000 kilometers for my tire, he is correct. He or she is correct. Are you getting it? So, what is the end result of your acceptance or rejection of a hypothesis is either the validity of a statement made by somebody, or a comparison, or a decision, or a final conclusion. Here the final conclusion is this, it comes from the same lot. Okay. The question could be slightly differently framed. A manufacturer claims that the average life of the tire is 40,000 kilometers, and when 100 tires were sampled, it can be like that. Is the manufacturer's claim valid? Yes, it is. If the mathematical process is the same, the question is worded slightly differently. So, understand the question properly, and here in the hypothesis, if you put 39350, you will be wrong. That is not correct. Okay. Yeah, see here, it is also called as student's t distribution. It goes up to infinity, it can go up to infinity. So, when do you use this infinity value? When the size is very large, sample size is very large, 1000, 2000, 10,000, 20,000, you can use these values, no problem. Okay. So, we will see one more example. The mean lifetime of a sample of 400 fluorescent light bulbs produced by a company is found to be 1600 hours with a standard deviation of 150 hours. Is the mean lifetime of the bulbs greater than 1570 hours? Test at a level of 1% significance and 5% significance. So, what is the question here? The manufacturer is claiming that the mean life of the fluorescent bulb is 1570 hours. That is their claim. Now, I have sampled 400 and I found that it is 1600. greater than what they have claimed. So, the question is, can I conclude that the mean time is actually greater than what is claimed? Is it greater than 1570 with 1% or 5% significance? That is the meaning. Okay, fine. We understood the meaning. So, now what is my hypothesis? H naught, that mu is 1570 and HA is mu is greater than 1570, because I want to prove it. I want to prove whether it is greater than 1570. HA is greater than 1570. So, T is 1570 minus 1600, okay, divided by 150 by 20. Why 20? I have sampled 400 minus, so I will get minus 4. Okay. Now, since 400 is quite large, I use the value corresponding to infinity, and you see at 1% significance, I will use one tailed because I want greater than only. So, I will use a single tailed. Okay. So, here it is, you can see the value here is at 1%, at 5% it is 1.64, and at 1% significance it is 2.32. This magnitude is greater than this in either case. So, I reject H naught. So, it is greater than the critical value, I reject H naught. Okay. I think we will make a small correction here. This is actually, the sample mean is 1600 and what I am claiming is 1570. The population is 1570. So, this is actually plus 4. Yeah, this is fine. Okay. So, this value I got, the T value is greater than the critical values both at 5% significance level and 1% significance level, it is greater. So, I reject H naught. I reject H naught means what? Automatically it means you accept HA. And what is my alternative hypothesis? My alternative hypothesis is the average is greater than 1570. So, I can conclude that the mean lifetime of the fluorescent light bulbs is greater than 1570 hours, even if I take it from a larger population. Got the point? So, you saw about the T tests. So, all along we have been doing one sample, and in the next video we will see how to do with 2 samples and how to use it when there is a effect on the dependent variable. So, continue with me in the next video. Thank you.